Again, thank you all for coming. So I'll start my lecture now. Everybody knows me, so I won't introduce myself. So this is partition identification for general distributions using multi-arm bandits. So paths are joint work with Subhashini Krishnasamy, and paths are related to the poster that Shubhadda presented it for the best arm setting last week. So the same ideas work here. Okay, so this is the problem. So we are given a collection of vectors. These are k vectors. These are all probability distributions. We don't know these probability distributions. You can call them arms, but we can sample from each one of them. And for the most part, 2 arms should suffice. So we can sample from this, and then we have this universe of these vectors of distributions. And the universe is finitely partitioned, I equal 1 to p. So our aim is basically we'll sample from these arms, these probability distributions that we can do. And quickly we need to decide which partition does this vector belong to. And we want to control the probability of error to less than or equal to delta. Explicit delta is given to us, and we want to explicitly control it with that probability. And with that constraint, we want to do these things as soon as possible, as few samples as possible. This comes from the motivation for. So is this problem clear? Yeah, one such new.
You're given
a new
distribution, and you have to figure out which partition.
That's right. That's right. And the reason we are thinking of many partitions is, think of this as nu is these distributions. You want to find which distribution has the largest mean. So this, one of this can be first distribution has the largest mean, or the second distribution has the largest mean, or third distribution has the largest mean. So these are your different sets, and you want to know which set this nu belongs to.
So are all the nu is supported on a finite set?
So I'll assume in the beginning, right now for lower bound analysis, I won't make any assumption. For upper bound analysis, I'll start by assuming that they belong to a single parameter exponential family, which could be finite or infinite, and later I'll generalize it substantially. I mean, it can be either way, it's arbitrary. The theory can be developed arbitrarily, but then we'll specialize to certain kinds of sets, explicit sets, and then we'll kind of work further. So some other examples could be, and the reason we look in this framework is because you see papers where they say, okay, we want to find the best few arms, best 3 arms, or a number of arms above a threshold, or below a threshold, or lying in some set. So it seemed that, a right abstraction is just to keep it at this level of generality and see what structures we get. And what we'll see is that there's an elegant kind of lower bound theory that one can develop, efficient lower bounds. It basically boils down to a maximum problem, and that maximum problem has a nice geometric structure. So we'll talk about all of that. And then the nice thing is, how do you generalize all of this to beyond simple distributions? People in computer science community generally look at Bernoulli arms, or more general single parameter exponential family. The nice thing about that family is that each distribution can be mapped to its mean. There's one-to-one correspondence. So you just look at means, basically. But how do you extend that beyond to more general families of distributions? So I'll talk briefly about that too. All right, so yeah, this is a classical problem in Monte Carlo, finding a distribution or best arm with the largest mean. Many distributions, models of transportation network, you want to find which model has least congestion. You can simulate from the model. Let's just carry on. So typically, your nu will, as you were saying, nu belongs to a particular set. And you're saying, am I identifying it correctly, or am I making a wrong assessment? So am I finding the right set A, or its complement? So really one can think of this for the most part as 2 sets. So Q comprises of 2 sets, A and A union A complement. And we want to find out if the vector means lies in a convex set or its complement. So for the most part, I'll focus on these kind of settings, that either my set of interest is a convex set, or it's a complement of a convex set. We'll see a lot of structure in that kind of setting. Much of what we say generalizes beyond this. Okay, so our agenda for today is we'll develop a methodology for computing lower bounds on computational effort for delta correct algorithms. So this involves exploiting the geometry of the problem structure. So this can be done using duality or minimax theorem in some settings. So I'll talk about that. And then we'll develop delta correct algorithms with matching computational bounds. So this is the kind of stuff that was already discussed by, Karthik, working with Rajesh. And we'll do this in the setting of half-space problem, convex and complement of convex settings. And then results are first discussed for single parameter exponential family of distributions. And then we'll extend it to this family. So this is basically, we look at all probability distributions kappa, such that under it, the expectation of function of the absolute value of the random variable has an explicit bound B. Now this function can be, just has to be superlinear. So fx upon x goes to infinity is all that we need. So in particular, this would work. So if such a bound is available, so this is what I guess J. Krishnan was trying to avoid, not have any information at all. But if you have this minimal information, if you're willing to live with the fact that all the distributions somehow belong to this family, you can say a lot more. Okay. So just, I've given some literature review here, but I'll probably save time and not go through this. The point to mention is that, this kind of work has been going on in statistics. You go back to Chernoff, 1959, and Albert, I guess, his student perhaps, 1961, and they wrote beautiful papers on this. Simulation community has been working on this over many years. And lately, computer science has been doing a lot of active work. So there's, thousands of papers coming out these days in the last few years. And then there's related regret minimization. So regret minimization for people who do bandits, they typically worry about regret minimization. Number of arms, you sample them in such a way that you want to minimize the average cost. But we won't focus on that. We'll focus on this delta correct algorithms. You stop at some point and you have delta guarantee of being, not wrong, making a mistake by more than probability delta. Okay, so let me just spell this out again. So they're given vector of k arms or probability distributions. We'll have an adaptive sampling strategy. So it looks at everything that's happened so far. A stopping time tau will be there. And at that time, a recommendation will be made, a subset from the partition that contains this vector that you're given. So you start with a vector from which you can sample. And an algorithm is set delta correct if for any mu of distributions, just the same thing again, it announces in finite time tau that mu belongs to some set aj with probability of error bounded over by delta. And this should be true for all delta greater than 0. Okay, so this lower bound is going to be key to all of this analysis in our talk today. And what's nice is that now we have this explicit lower bound. This was not known until 3-4 years ago. So it relies on change of measure arguments that go back to at least Lai and Robbins in 1985. And this is, just what is the lower, given that your algorithm has this delta correct properties, what lower bound does it impose on any instance of vectors, of distributions? So suppose I have mu, which is these k distributions which belong to set ai, and nu, which belongs to ai complement. So now imagine your algorithm as a judge. It is seeing all these samples coming out. They look like they're coming out from this vector mu. But it's wondering that, as somebody was saying, it's wondering that they could be coming from nu. It needs to be sure that they're not coming from nu. So that suggests this distribution separation inequality, that expected number of times under mu, arm I is sampled, times the distance between arm I under mu and arm I under nu. This is measured by the Kullback library between mu I and nu I. If you sum this this has to be greater than or equal to log of 1 by delta. So it's an explicit non-asymptotic inequality that exists. This has to be true for every nu, which is in AI complement. So that gives us a handle on this problem, basically. Let me just show you the rationale for this. So suppose, this is all data-driven. So I see this data x, xij, for each arm k, I see nj samples, and that's when I stop. Okay, so this is an adaptively generated sample by delta correct algorithm. Suppose the data came from underlying distribution mu. Then my algorithm will say that this x belongs to set ai, so mu is in ai, x belongs to ai, and it would say this with probability at least 1 minus delta, right? And if we look at under measure nu, if the data was coming from measure nu, which is in ai complement, then this data, the algorithm will say that this data belongs to ai with probability at most delta. And now we can re-express this probability under change of measure, under measure mu, and this is just the likelihood ratio. I've just exponentiated it, right? And there's an indicator function here. If you allow me the fact that this indicator function, if you're just that generous with me, that because under mu, this event has high probability, if you allow that this has probability 1, then just by Jensen's, you see that this follows. Right? This expectation just comes upside. You use Wall's identity. NA number of this should be, this is NI, mu NI into this Kullback library. So this just follows from here, right? So it's, so it takes a bit of skill to get rid of this indicator function, but that's all there is to this. But you get this non-asymptotic inequality, right? So this holds, this is, that's going to be always true. And what we do with that is, so now if you want to get a lower bound on our algorithm, so recall the sample complexity, the amount of number of times the arm is being sampled in expectation, is just sum of this E mu of Ni. So I'll just put a variable here, Ti, and I will minimize all the overall space of Ti's which satisfy this constraint. And this constraint has to be true for every nu lying in AI complement. Right? So that's an optimization problem I get. And then the solution to this times log 1 by delta, so I just put 1 here, gives me a lower bound on my algorithm. So that's a lower bound I get. So now I just have to analyze this. Mu belongs to AI again. This is all the nu which don't belong to AI. So what I'll do now is I'll just re-express this by dividing by summation Tj and multiplying by summation Tj. So I just re-express this constraint. And the point is minimizing this subject to this constraint is same as maximizing this guy here. In the space of Ti is now restricted to a simplex. So I get this max-min problem. So I'm looking at this infimum over nu in AI complement, this quantity here. This is a separation between mu and nu. But basically think of this as a game. You as an algorithm designer chooses your WIs, how many samples I want to give to each arm I. That's your choice. Once you've chosen those, the nature picks the worst case, the most difficult distribution to separate from AI complement. So nature picks that, and that's the problem that you have to solve now, basically. That gives you the lower bound. So is this clear? Any questions? So your each AI partition will be either 1, 2 arms have the largest mean, or 1, 3 arms have, each ij arm has the largest mean. So you have, k into k minus 1 by 2 number of partitions. I mean, right now we are saying in that case, now you're, suppose your mu belongs to a particular category where arm 1 and arm 2 have the largest mean.
Okay.
Then your AI complement is all the other, vector of distributions where top 2 arms are different from 1 and 2. So you'll have to solve this optimization problem to get a lower bound on that. So right now I'm not giving the algorithm, but a lower bound on the algorithm. So this times log 1 by delta will be the lower bound. And now the question will be, how do you design an algorithm which matches the lower bound? So how do you sample from all of this? So that I'll come to. The guidance from that will just come from solving. If you knew mu, and if you were able to solve this, then the solution W star tells you exactly how you should sample each arm. So that it's as simple as that. Now you don't know mu, so you learn mu. And you plug it in. That's the algorithm.
One sample from one distribution.
That's right. So you explore a little bit on all the arms, sublinear amount, so to speak. So you have a fairly good idea what the means might be, and then you plug them in the lower bound in this problem. And now you try to track the solution W that you get. That's going to be the flavor of the solution. But that's all the game I'm revealing to you right now. Okay, so now this is fine. So this is a lower bound problem. There's no restriction on distributions right now. AIs can be arbitrary sets. My nu can be arbitrary collection of probability distributions. Everything I've said so far works in this generality. But some restrictions are necessary on the distribution of underlying arms. Let me just give you an example. This is from Glenn and Juneja 2015. So suppose I have a delta correct algorithm, which works on these two distributions. This is distribution mu1 with mean m1 and distribution mu2 with mean m2. m1 is greater than m2. It also works on another instance of two distributions mu1 and mu2, where now under mu2 the mean is m3, which is bigger than m1. Meaning the algorithm in this case will say mu1 has the largest arm with probability at least 1 minus delta, but in this case it'll say mu1 has the largest arm with probability at most delta. So that previous inequality which I showed you will apply. These two instances differ only in these two arms. Right? The second arm basically has a different distribution. So what that gives you is that the number of times arm 2 must be sampled under mu times the Kullback-Leibler distance between mu2 and nu2. That must be greater than or equal to log 1 by delta. Right? So this just lower bound follows. Any delta correct algorithm has to satisfy this lower bound. Now, because nu2 could be any distribution which has larger mean than under mu2, so I basically take an infimum over all distribution nu2, so that I guess this should be m2. m3 is greater than m2. This is the mean here. So this is my lower bound on number of times arm 2 must be sampled. So basically what's going on is, that's what I'm coming to. Everyone's stealing my punchline. But that's exactly right. So, I think this must be well known, but nonetheless, this is a point being made here, that unless you assume some kind of restriction on the underlying distributions, this expectation is going to be infinite. So Glenn and Jay show that if distributions are unbounded, then this Kullback-Leibler distance between two distributions can be made to be arbitrarily small, although the means are arbitrarily far. So that just makes the problem difficult to solve. And so some restrictions are needed. We're just motivating some restrictions. You can't do without some restrictions. And then we make minimal restrictions. So this here, the idea is, okay, green is your true distribution. Now you just take some mass from the beginning and throw it in the end. This is the red distribution that you get. And you choose this point and this mass carefully, and you can achieve this fact that the means are arbitrarily far and Kullback-Leibler distances are arbitrarily close. Okay, so now I'll go ahead and start solving the lower bound problem. But first I'll restrict myself to one parameter exponential families. So I won't show the form or distribution, not relevant, but the distributions we have in mind include binomial, Bernoulli, Poisson, Gaussian with known variance, gamma distribution with known shape parameters. So these are instances of single parameter exponential families. The main character of them is that mean is all you need to identify the distribution. So for this part of the discussion, I'll replace the distributions with their means. So this allows us to think of Kullback-Leibler divergence as a function of the means of the distributions. So in the remaining, most of the talk, Q is a collection of vectors of parameters in R of K now. Okay, so now let's characterize the solution to lower bound when sets A and A complement our half spaces. So I'm given this vector of distributions, and I'm given a half space. Does it lie on this side of half space or that side of half space? So same thing. So mu is in A corresponds to this half space here. AIs are given to me, B is given to me, corresponds to this half space. Essentially, I'm asking for the lower bound, what restrictions do all the nus which are in A complement impose upon the amount of times each arm should be sampled under mu? Right? Okay, so let me just give you some geometrical interpretation for this. That's quite nice. The problem just suddenly simplifies a great deal. So we're trying to solve this min-max problem, right? So let's fix the weights here, W. Let's just look at this quantity that we're trying to minimize here. So if I take my nus to be equal to mu, then this quantity here is 0. And just to, I'll be talking about level sets, but just let's assume for now that, I'm looking at Gaussian distribution. So mu1, mu2 is 0, 0, centered here, two distributions. So the level set of this is just an ellipse, right? And I'm trying to now find the minimum ellipse. I'm trying to find a nu in A complement which minimizes this. So essentially you can think of this ellipse right now of this sort. These are all the points in A complement with the corresponding value of the ellipse C. And now you shrink the ellipse so as to minimize this C, and you'll basically shrink it until you just touch this half plane. So that kind of gives you a feel for, okay, for any W, what will the solution look like? It'll just be an ellipse which is tangential to A complement here. And now, what's nice about this problem is that no matter what the form of A complement, this is a concave function of W, right? It's a linear function of W here, and infimum of linear function of W is going to be a concave function of W. So it's a concave programming problem. So if I were to solve this for, for a given W, I can do some kind of gradient descent and move towards the optimal. This is nice because I can do this not just for one half plane, but I can do this for if this was a union of half planes at the outside. So if my A complement was a complement of a polytope, I'll just find the nearest, I'll look at all the half spaces and find the nearest one and then do gradient descent and keep moving. So it's a proper algorithm which works in great generality. It would also work if my A complement was arbitrary set, basically. But you have to figure out a few things then. So let's move on. So let's just solve this problem now. I haven't told you what the W's are, so let me just show them right now. So again, we are solving this max-min problem here. So because A complement is a convex set, with some kind of compactification, you can show that one can use min-max theorem. So science min-max theorem can be used. So then, this just becomes infimum over, so it's just a saddle point, right? You can first minimize and then maximize, or you can first maximize or then minimize, you get the same answer. So it has a very nice geometrical picture to it. In any case, so I'll do this now, infimum nu over A complement, maximum of this quantity here. And this is a linear function, so I just basically, I pick up the maximum value, A, which maximizes this. So this is just a min-max problem as follows. So choose a nu in A complement set, which maximizes the, over all arms, the Kullback-Leibler distance, which minimizes the maximum of this thing here. So let's just see this pictorially. So let's look at the setting where I again have two Gaussian arms, mu1, mu2 is equal to 0, 0. Kullback-Leibler distance now just becomes nu I square upon 2 for both the arms. These are Gaussian with variance 1, both of them. So now suppose I start at this point. So I'm going to look at maximum of the two Kullback-Leibler distances, max of these two. So I'm at this point. I follow the steepest descent to minimize this. I want to minimize the maximum. So I come up till this point. At this point, both are equal. So now I'll come down to minimize the maximum. So I come at this point, and that's my solution, basically. It's as simple as that. So this solves the problem. Now, the same thing works in generality. So the solution W star, nu star will have the property that this Kullback-Leibler distance at the optimal point will be equal for all the arms. And in addition, you'll be at the half-plane boundary. This would basically identify the nu star for you. To find the W star, you have the slope matching condition, that the slope of the ellipse at the optimal W has to match the slope of the half-plane. And that gives you the condition to actually find these W stars, basically. So you have the whole solution. There's an elegant geometric, and then you get this lower bound problem, lower bounds on the problem, basically. It's just one of these things. Inverse of that times log 1 by delta. All right, so now before I go and talk about convex sets and other things, let me just tell you what the algorithm would look like that matches this lower bound. And here we are kind of relying on some work done by, on the best arm setting by Garavier, Kaufman in their paper in 2016. So we kind of build upon their idea. So, but the big picture is as follows. I'll just give you a big picture of this, because any of, if you follow this recipe, the details don't really matter. So the decision is which arm to sample and when to stop, right? That's what an algorithm has to decide, what arm to sample next and when to stop. So so that's what I just mentioned. So that sampling step n ensure that at least square root of n samples are allocated to each arm. Essentially, there's some exploration being done. Nobody's being starved. You're not giving linear amount of samples. That's too many samples. That's wastage. But you're ensuring that nobody's being starved and you're not making bad decisions because of random chances. This ensures that with high probability, the mu hat n. See, now we are only looking at single parameter exponential families, so means are enough. So we're just estimating the means, basically. So mu hat n approximates mu. And since that's the case, now we go back to the lower bound problem, plug these mu hats n's as proxies for mu, so this empirical means, and we get W star mu hat n's. And now that we have this, we come up with an algorithm which closely kind of tries to match these fractions that we have. And that's it, basically. Just do this, and that's going to work. All right, and then you still need a stopping rule. And most importantly, you need this guarantee that the probability of stopping wrongly is less than or equal to delta. So stopping rule goes back to Chernov's time. So this was also mentioned by Karthik earlier. So after iteration n, suppose mu hat n belongs to some set A tilde, either A or A complement. Right now I'm just keeping it two sets. So compute the logarithm of maximum likelihood value over the set A hat, basically over the whole space. What measure explains the data the best in the whole space. And then you get a hypothesis from that measure that tells you that it belongs to A tilde. Then you look at A tilde complement. So under the alternative hypothesis, what measure is the most likely one explaining the data. So you look at this ratio, and if this ratio becomes large enough, that's when you stop. And the skill goes in developing concentration inequalities to show that the fact that you'll have a deviation from the norm, and that probability can be bounded by delta. So I'll come back to this a little bit later in a more general setting, but this leads to something like this. And then, your algorithm will be something like this, that, at any time you have mu hat n's, this is your ratio that you had, the log of the ratio. You compute the infimum of this over all A tilde complement set. In any case, and then there's some separation function. Let's ignore all of this. But basically, if this thing is large enough, you stop. I'll come back to this a little bit later. So that's the flavor of the algorithm. The main thing is, with this kind of algorithm, you actually get that the sample complexity, the amount of samples that you generate, expected number of samples that you generate in this algorithm, divided by log 1 by delta, converges to the appropriate lower bound as delta goes to 0. So at least as delta goes to 0, you're as good as you can be. You're matching the lower bound. Now, it's a big open problem, by the way, if somebody's looking for these things, how to get these guarantees non-asymptotically when delta is finite. So that would be a nice contribution in a way that, but all of these algorithms are very conservative, so one has to think about these things as well. Okay, now I'll come back and talk about a more interesting case when my set A or A complement is convex. So again, the big mantra here is that just focus on this max-min problem, right? For any set A complement. This is what we are trying to solve, this max-min problem. We solve this, we get the lower bound on our problem at hand. So now this is the characterization when A complement is convex. So I don't know if I have a picture of this. Yeah. So my mu is here and A complement is convex and all of this is A, let's say. So the solution W star nu star has the following characterization. Nu star uniquely solves again the min-max problem. Because again A complement is convex, I can use my science max-min theorem. Right? There exists a maximal subset I of these arms, so that only on that subset will you give positive weights. W star I will be positive. The remaining subsets will get a negative weight. So what that means is that the lower bound is telling you that you should not sample all the arms, but a subset of arms. And that subset has the property that on that subset, this Kullback-Leibler separation is going to be constant across arms. And the arms which you're not sampling would have been more difficult to separate. It will be lower than this constant. So the lower bound is basically telling you don't sample the arms which are difficult to sample, only focus on the arms which are easy to sample, and don't separate from the set A complement, separate from its projection. And that turns out to be the way you achieve the best projection. W's are up to you. So you choose your W's in such a way that you've identified what's the best way to kind of cheat the system, so to speak. Is this clear? So you won't sample all the arms, just a few arms, which has this nice property that the ones which you are not sampling are much harder to separate compared to the ones which you are sampling. So let's just see a picture to make this point home. So suppose, again I'm going to solve so the proof is again going to be like, I can interchange max and min. It's exactly as I said before, just that now, when I maximize this, I'm looking over, I have to worry about the fact that news lies in a convex set, not in a half space. So let's just see here. So again, I'm at this point, I have two, this is Gaussian setting, mu1, mu2 are 0, 0. This is the Kullback-Leibler distance, this is the maximum of the Kullback-Leibler distance. So again, I come down the steepest descent line, so I come to this point. And I can again improve by going down this line, so I come to the boundary. And now the only way to improve is to go across around this boundary. I come here. At this point, nu2 star is bigger than nu1 star. So that tells me that I should only focus on nu2 star. At this point, only the Kullback-Leibler distances which are equal are the ones which I'm going to sample on. Ones which are smaller, like this one is smaller, I should not sample on. So basically what I should do is just sample the second arm and try to separate it from this line here. Whether it's above this threshold or not. That's all I need to really do in this case. So what it's basically saying is, from an algorithmic point of view, that I'll generate some samples, I'll see both the arms. It'll become clear to me with large probability that really what's important is just the second arm. So that's the only arm I should sample. The first arm only should get sublinear amount of samples. That's the observation one gets from here. Okay, now when A complement is a union of half spaces, so when A complement is a complement of a polytope, so this is, we covered when A complement is convex. Now when we look at A complement is a complement of convex, I'm just looking at union of half spaces. Just keeping it as simple as that. So something like this, so A complement is this. So there, we just have this algorithm right now. This is an area where we are, we plan to think further. Where you fix your W, you draw an ellipse, you can find out, what's the solution if you just had any one of these hyperplanes. So you find those solutions out, take the smallest ellipse. Basically what you're doing is you're just growing the ellipse until it touches any one of these. Once it touches that, at that point you find the gradient. It's a concave programming problem. You get a new W and you repeat the whole algorithm. And that would converge. But this needs, this needs a lot more work, particularly when A complement is very general. Okay, so let's just move on. So let me just say this here. So recall the min-max lower bound problem is given as follows. So given WAK, we solve this problem, and this just means, as I mentioned, expanding the ellipse till it by finding the nearest hyperplane, and then you use steepest descent. You update your WAs and just keep on going across the improved values of W. All right, now let's talk about general distributions. So this was all which worked when the distributions were nice, single parameter exponential family. Now let's assume that our distributions have this following constraint, that there exists some function f. So that f of absolute value of x is bounded by b. B is known to us, f is known to us. So f could be x log x, for example, right? So this is known to us. Now how do we devise algorithms? Okay, so consider set A of the form where all the distributions now belong to L. L is the family which I just showed you. It's a compact set of probability distributions. That's easy to show. It's closed compact set. And the means of these distributions belong to B, right? So now I'm going to look at this problem that, given that my mu belongs to this set here, this is my lower bound now. So sigma k is just a simplex in which W takes value. I have to take infimum over all x. X is an RK lying in B complement. So B is an RK here. So I have to solve this problem. Main thing is that, earlier I had I've not made these slides well, but, earlier I had KL, KL distance between two distributions here. Now I'll bring the infimum inside and I get KL inf here. Essentially, I take an infimum over all distributions which have mean xi, right? So once I define this new quantity KL inf, then this is my new min-max problem, and my x's are still taking values on the real line. Each xi is taking value in the real line. Where this KL inf is now defined as, I'm looking amongst all distributions which belong to my set L, which minimize the Kullback-Leibler distance from eta distribution. So eta is fixed now, and the mean is given by x. Right? So it's a solution. KL inf is a solution to this optimization problem in the distributional space. What's nice is again that I can use duality and get alternative representations. So that becomes very useful. But I have this. What's nice about all of this? Let me just say it in the next slide. So similar definition KL inf was seen for bounded random variables, not the set that we are looking at, by Bernitas and Katehakis in 1996 and Honda and Takamura in 2015. And they used this in the regret minimization setting. So this definition did exist. What we do show in our general setting is that KL inf eta x is a convex and twice differentiable function in x. And it's continuous in eta in Wasserstein distance. So it has the nice properties that we are looking for. In particular, since it's convex in x, everything that I said earlier, when this was a convex function of x here, when I had nu here, which was a real valued parameter, is also holds in this setting. So all the geometrical story that we had is true in this generality as well. Nothing changes. This is still a strictly convex function. So all the ellipse which I showed you and the way we solve things, everything still works. Okay, so that's so analysis of lower bounds is identical to earlier one with KL inf mu I x replacing KL mu I eta I. So anyways, let me just say a few things. What we can do is, the problem now is when we are going to, we need to solve this lower bound extensively to have an upper bound algorithm. So we need to be able to compute these things. So for that, this dual representation becomes quite useful. So KL inf eta x, recall this is, again, it's a solution over all probability distributions which lie in the set L. Let me just recall for you, L is given by this expression right here. So we are going to minimize over all distributions lying in this space. And we'll have this linear constraint that the mean is going to be equal to x. That, with duality, you can show is going to be, maximum of this quantity. So it's an expectation under eta. And x now has, x has distribution eta, and lambda 1 and lambda 2 are parameters. And they belong to this compact set. That can be shown. So you've reduced it to a problem in the space of parameters. It's a much easier problem to solve. So what one needs to worry about, we are going to have the same kind of stopping rules that I showed you earlier. Earlier I had Kullback-Leibler distances, now I'll have KL inf. What one worries about in these stopping rules is that somehow they take a large deviation and make a wrong decision. To control for that, we have to develop concentration inequalities. So in particular, we show that if this kappa hat eta n is an empirical distribution, sample from distribution kappa, then the probability that this term here takes a deviation. Now it can be shown that when I put kappa here and this is mean of kappa, then KL inf, just like the Kullback-Leibler distance, is going to be 0 at its mean. But what's the chance that the empirical mean, if an empirical distribution when plugged here, gives a large value here? There's a large deviation taken of this sort. So what's the probability that this happens? Now we need to develop an explicit concentration inequality which is true for all distributions lying in L. So this inequality, this exponential decay, I have a polynomial term here, and that's true for all distributions lying in L. So it's a uniform kind of a probabilistic bound. So that requires a bit of work. But duality helps basically. Duality reduces the problem to just kind of looking at these two parameters. So you want to say the maximum of the, when this is computed for empirical distribution, the maximum does not take a large value. This can be shown to be a nice concave function. So you can make a grid, and you can, if the grid is small enough, it's very easy to control the maximum. So that's, the fact that you make a grid gives you this polynomial term here. But for each term, if I didn't have this maximum here, if I look at empirical distribution of this, and I ask what's the chance that it takes a large deviation, that can be uniformly bounded by e to the power minus nu. So that's a uniform bound, and we are willing to accept polynomial terms here. So that's why this works. Okay, and then you need something more because our stopping rule, if you remember the earlier one, will have the following flavor. I'll just say this. I just want to show you this inequality, but it becomes useful because it comes up in the stopping rule. So now I'm summing over the number of arms, over the arms, and this is the number of time arm A has been sampled over a total of n pulls. This is Kullback-Leibler infimum. The fact that the sample, the empirical distribution separates from its mean. What's the chance that this summation here takes a large deviation? One can again come up with an explicit kind of a bound on this for all distributions belonging to family L. So with these, you can control the probability of error. You can look at the set where after you stopped at the time when the empirical mean was in a different set, and you can actually show that that probability is going to be controlled by delta for all distributions.
So what is this d hat?
D hat is just a constant. It's not a function, it's just a constant here. Okay, so that's all I have to say. So we consider pure exploration multi-arm bandit problems in a general unifying framework. This involves finding the correct partition for a vector of distribution from a superset of such collections. Right? That's how we started. We developed geometric and duality-based methodology for computing the lower bounds on computation effort for delta correct algorithms. So I showed you this to you for some geometry, but it's kind of clear what one would do for more general sets. I think the recipe is here. So using these, we develop algorithms with matching computational bounds, matching as delta goes to 0. I should add that, and we extend this to general distributions. The broad point here is that, these concentration inequalities, in some sense, are quite conservative. In the sense, so this is quite loose. And what that means is that you're stopping much later than you should be. So typically the lower bound and the upper bound can be 15, 20 times away for a reasonable delta, or even more sometimes. So in any case, that's an issue. Can one do better by maybe developing better explicit concentration inequalities, or maybe changing the criteria of evaluation as you were trying. Thank you.